Hello everyone and welcome to my channel. My name is Aryan Movahedi and today I want to start a video series on the fundamentals of circuit analysis to help students and hobbyists in getting a glimpse into the world of engineering and the methods and tools used for solving such problems. So let me tell you a little bit about myself so that you get a feel for who your instructor is. I'm currently finishing my sophomore year in electrical engineering and I'm a tutor in physics and computer science at my school. And basically my goal is to share some of the ideas and skills that I've learned so far with anyone who's curious or interested in the natural world and specifically the subjects of mathematics, engineering, and the physical sciences. So some of the interests that I have, as I mentioned, physics, engineering, mathematics, and also chemistry and biology. But then some of the things that I tend to think about quite often include mathematics as an abstract tool that can be used for describing the natural world and maybe some of the limitations that it has. And some of the other things include motion of objects, electronic communications, forces and fields, control systems, space technologies, education and raising interest in science and technology, and similar ideas. So now that I told you a little bit about me, let's consider some of the questions that some people may have in first starting a class. And some of these questions are the following that I had when I first started a class in circuit analysis. So the first question here is, what is electrical engineering? Well, in my experience and what I've seen so far, the goal of electrical engineering is to use physical principles and properties of matter in order to transfer energy from one point to another or communicate from one point to another. And it'll become more clear as we go along in this class as to what are some of the applications of it and what are some of the other goals that electrical engineering has and the tools that it offers us. So the second question is, what is circuit analysis? Circuit analysis is basically a set of methods and skills guided by mathematical and physical reasoning in order to study the behavior of electrical quantities and make quantitative predictions about such behaviors. There are a few important points there. One is that what we're trying to do is to get an insight into systems that can be modeled from the natural world as electrical quantities and be able to understand the inner workings of them and make quantitative predictions, meaning we're going to predict what's going to happen given time or a certain frequency of an input signal, and be able to basically use mathematical rigor and reasoning to be able to come up with a way of describing what's going to happen given a certain frequency or given time. So those are two important points, quantitative predictions. So the third question is, why should we care about this course? Well, if you're interested in electronics and electrical engineering in general, it's good to have a decent background in circuit analysis and be able to understand the physics behind it, so that if there's any errors or troubles that you have with your circuit, you're able to diagnose it and are able to even design your own circuits. Because without this set of skills, you may not be able to have the good solid background to be able to do diagnostics and designing and things of that nature. And the fourth question is theory versus applications of this class. Well, what is the difference between theory and application here? Well, I want to remind you from a physics or a scientific perspective that the universe is complex. If somebody attempts to try and understand a dynamical system fully and at once, well, confusion is going to take place. The person is going to be confused. So generally in engineering and science, we want to make simplified models to gain a basic insight into the inner workings of a particular system without getting too confused about it. And in particular in electrical engineering, once we have a basic understanding on a particular topic, we can then experiment in the lab and tinker with the measurement devices and understand ways of dealing with uncertainties in measurement and reducing them, and also finding ways to make things simpler. Let's see then, going into an experiment blindly without prior understanding of the topics that we're going to talk about kind of makes it so that we lack an understanding of the subject, and it will lead to confusion and a lack of appreciation of what's going on physically. Okay, so the last question being here that what are the benefits of learning this course in this class? So a few of the benefits that I would list include problem-solving abilities using mathematical skills, ways to think about topics that you may have not known about before, for example, alternating current or voltage and power and how it may differ in a direct current system versus a sinusoidal system, which we'll talk about in depth later on. Another benefit being that it's going to help us in future electrical engineering courses and sub-disciplines once we have a firm understanding of the basics topics, because as you know, as you may or may not know, it's going to be basically a branch. Once we learn the basic ideas, everything is pretty much going to be a sub-discipline that's developed based on a particular topic in the fundamentals of this class, as far as electrical engineering goes. So understanding it and having a firm grasp on the ideas and some of the measurement techniques and ways of dealing with them in the laboratory is going to be very beneficial to whoever is going to pursue future classes in electrical engineering and computer engineering, of course. Not to mention, other physical sciences and being able to have the basic understanding of how to go into the laboratory. Another thing that's going to do is it's going to finally help you understand some of the systems that you may have not understood when you were a kid. And I had this experience when I first took this class. There were a lot of things that I wondered about how they work when I was a kid, and I understood them once I took this class. And then the last but not least being that it just makes you look smart and knowledgeable to know some of these things. So if not for anything else, that should probably be good enough reason to at least see if you like the next few videos and see if you can follow the class. Well, if you have any other questions that I didn't mention up here, some fundamental questions about this class, you can go ahead and either comment below in this video or email me at this email. It's persianengineering96@gmail.com. I would love to help. Don't be shy. I like to help and clarify difficult concepts. So here, let's go over real quick what we need to be familiar with in order to pursue this class in a rigorous way. You can always sit back and watch things, but as a professor in Yale says, you can either learn about it or you can actually learn how to do it. So if your goal is to actually learn how to do the skills and learn them and what we're going to do here, I recommend kind of reviewing some of the ideas in algebra, trigonometry, calculus, differential equations, and a little bit of linear algebra when it comes to linear equations and a system of equations. And another thing is in science, if you know your basic electromagnetism and physics and also a bit of Newtonian mechanics, because you'll use some of those basic mechanical ideas to explain some of the more difficult concepts in electromagnetism. So that'll be beneficial. So after that, then let's look at the content of the class and what we're going to go over. The first part is going to be about DC circuits or direct current circuits, where the quantity of current is not going to be rapidly changing. It's just going to be constant. And what we're going to go over in this section is going to be the basic concepts, so current, voltage, power, and then some of the basic laws, such as Ohm's law, which is a very basic law, and it's not a physical law of the universe. It's just an approximation that tends to work for a range of currents and voltages, given that the temperature is not changing much. And then we're going to look at methods of analysis, so nodal mesh analysis, which is an engineering way of applying Kirchhoff's current law and voltage law. Then we're going to look at some circuit theorems, so simplifying some of the methods of analysis and kind of getting a more deeper insight into the behavior of such circuits. Then we're going to look at some fundamental devices such as operational amplifiers, which are used a lot in analog and some digital circuits, and we're going to see how we can work with these. And after that, we're going to look at capacitors and inductors, which are two fundamental passive components that are pretty much the basis of electrical and electronic circuits. Then we're going to look at first order circuits, which are, the reason it's called first order is because the behavior of these circuits are characterized by first order differential equations. And how they're produced is basically by putting resistors and inductors and or putting resistors and capacitors together, and the behavior is going to be in such a way that you'll need differential equations, and algebra no longer is sufficient for describing the behavior. After that, we're going to look at second order circuits, which are which occur when you combine resistors, capacitors, and inductors together, which we'll see can be really helpful and is the basis of communications and control systems. In part 2, we're going to look at AC circuits, which are phenomena where your current or your voltage is not constant and is changing kind of like a sine function or cosine function, going back and forth with time. It's not constant with time. And what we're going to look at is sinusoids and phasors, so kind of simplifying the mathematics behind it to be able to describe it in a simpler way and not have to use trigonometric identities every time we want to do a simple calculation. Then we're going to look at sinusoidal steady state analysis, which is basically saying after a long time that a switch has been thrown, we're going to see how the circuit behaves. And then we're going to look at AC power, which is basically the mains at your house when you connect something to it. What's happening to the power, what's happening to the voltage and current. And then we're going to look at three-phase circuits, which will make sense once we talk about AC power and kind of magnetism and such. Then we're going to look at magnetically coupled circuits, which is the first part where we start talking about how circuits behave or respond to each other when you have what's called a magnetic flux change occurring between them, which kind of requires a background in electromagnetism to fully understand what's going on. And after that, we're going to look at what's called frequency response, which is what happens as you increase or decrease the frequency of the input into a linear system. Okay, after this part, we're going to look at some advanced circuit analysis topics, which include Laplace transforms, which, if you've taken differential equations, you'll see that Laplace transforms are very useful in that they turn somewhat hideous second-order differential equations into simpler algebraic equations. And after that, we're going to look at the applications of Laplace transforms in circuit analysis, and also going to look at the Fourier series and the Fourier transform, which basically the Fourier series talks about how kind of a weird-looking signal, such as what I'm about to draw here, for example, some signal like this, can be composed of simpler sinusoidal signals. This is kind of a mathematical tool that is used quite a lot in communications and signal processing, and wherever you have a signal that's composed of many different frequencies. And after that, we're going to look at two-port networks, which kind of changes in the way that what we looked at before then, everything up to this point would have been composed of like two terminals. So like a terminal A and terminal B, some current going in and some voltage across the two terminals. Whereas with the two-port networks, we're going to have multiple ports, and we're going to see how the laws that we learned in the previous laws and methods that we learned in the previous chapters apply in multiple port networks. Okay, so in this next video, I will talk about some of the basics we need to know and some of the ideas and, for example, abstractions that we're going to use to be able to go forward with this class. See you in the next video.